Thanks everybody here for coming to this session. My name is Yan Bo, and I'm an Apache Spark committer, and currently work at HadoopWorks. This talk I will co-speak with Wang-Da Tan, Apache Hadoop PMC, member also work at HadoopWorks. We will show how Hadoop ecosystem boosts the TensorFlow and machine learning technology. We will give mainly three parts of our talk. The first part is I will give the overview of machine learning on big data platform. And then Wang-Da will talk about how Hadoop yarn boosting machine learning workload. And finally, I will give a very simple example to walk through how to resolve a typically machine learning problem like
I can't hear because it is a microphone. So probably it's mine is on, but yours is off.
Really?
Closer. See?
You can hear me? It's better? Okay. Okay. I think my clothes is not better to plug this microphone. So I will take it in my phone, in my hand. And then finally, I will give a very simple example to walk through how to do a typically machine learning problem, it's called CTR prediction problems on the big data platform. Okay, let's start with the first part. You can say, as the data is becoming more and more bigger, and we need to train a model for machine learning of our data scientists. We need to train a better accuracy model. Usually, a big data and a large model will mean better result. So this is because we have Hadoop to store large-scale data, and we can use Hive on Yarn or Spark on Yarn to processing this kinds of data. And then we can use a lot of machine learning frameworks like TensorFlow or Spark, MLlib, or XGBoost to training model on this workflow, on this platform. And another trend is the change in roles in machine learning. This is different from the original single machine area. As increasing the data size and the problems is becoming more and more complex, so one person can't finish all of the work. We need data scientists to work together with. We need data scientists to work together with. Oh, sorry. Okay, we need data scientists. Okay, we need data scientists to work together with software engineer. Usually, data scientists will start to explore data and to create a basic machine learning pipeline and to do some performance or evaluation, or to judge by some machine learning metrics and find the best machine learning pipeline. And then they will push the work to the software engineer. They can load the model that get from the data scientist and then deploy the model, make prediction, and online service. And the input data for the software engineer or for the model serving usually can be batch or streaming. This is a challenge for a data system. So let's show the basic machine learning pipeline. Usually several steps. The first step is data pre-processing and feature engineering. And second is model training. And the last step is online serving. The most important thing is to get a better model or better result for your question is you should choose the best features and the best model. We can't say it's best. It's the best suitable for your questions. So usually the workflow will first get feature representation from raw data, and then feed this data, then do some feature pre-processing to get features, and then feed the features to model training and get the best model during some model evaluation, model tune or parameter tuning, and then we will push it onto service. The machine learning workflow looks like it's very complicated. Usually involves several steps like the picture depict. So we need involve a lot of components during the whole machine learning process, especially when you train a model on a distributed environment. So just like the picture depict shows, only a tiny fraction of the code is actually devoted to model training. You can say it's only part of the very tiny fraction of the whole process. So it usually need a lot of support from the infrastructure. You can say in a lot of companies, especially internet companies, we will need a platform, and then a lot of data scientists and machine learning engineers can do their jobs. So let's find out the big data infrastructure step by step, how it can help the whole machine learning steps. First, for feature preprocessing, usually we will load data from Hive, from HDFS or database system, and then we join data from different data sources to generate a wide table, and then this is Hive and Spark is usually used for these steps, and then data scientists will start data exploration with Zeppelin, and at last we will show the examples under Zeppelin, and then random split the data for training and test using Spark. After that, we have the basic data, and we will put the data, transform data to features. We have typically two ways. In the first way is we will do by handy design is feature transform or selection. We can use Spark. Spark MLab has a lot of transformers to do this. And for the deep learning, it's very hot topics. We can learn some features by automatically. So feature embedding is also very cool technology and very useful technology to learn features, especially the feature is very hard to design by handy. After that, we have the features. We will feed the features to model. Typically, we have two kinds of models. The first kind is traditional machine learning models, and another is deep learning models. Deep learning is so hot, but it's not fit all problems. For the traditional machine learning models, like linear models or gradient boosting tree or others, and we can use Spark or XGBoost, very popular at Kaggle competition. And for deep learning models, like CNN is very useful in image processing, RN very useful in speech or in speech recognition or natural language processing. And TensorFlow or MSNet useful for deep learning. And BigDL is another deep learning library built on CPU. So some users may have requirements, but it's not the mainstream. Yes, deep learning can't fit all. For the problem set is here, only parts of them can be solved by deep learning, or we can say parts of them are solved perfectly for deep learning, and others, like recommendation and the CTR estimation, usually will use a lot of other models, like linear models or like gradient boost tree. And for some topic models or PageRank, we still need the graphic engineering. So, and especially some hybrid model, like the model Facebook have proposed to combine a gradient boost tree and a linear model, we can get a better result. So after we have the model, we will do model serving. Before the model serving, we should do experiment offline or online, and then we deploy the model. Especially your input data is very, very big. You need to deploy the model distributed and to parallel model serving on batch data or on streaming data. And this is the whole step of machine learning on big data platform. Okay, and then I will talk about how Hadoop Yarn can help us to achieve the requirements that I have proposed.
Yeah, so thanks, Yambo. So can you guys hear me? Cool. Yeah, so I'm going to start. So on one machine learning platform, which is on top of yarn, what it should looks like. So first you have some hardwares like the CPU, GPU, and SSDs. Then you need some data, which is stored in the HDFS, S3, or RDBMS. And you have some requirements to run the jobs. So you need the Hadoop yarn. On top of that, you may need to run some normal batch jobs, the ETL job, like the Hive LLP or the Spark. In addition to that, you need some machine learning requirement. So you want to run Spark, Distributed, and TensorFlow. So on top of that, you need to run Zeppelin notebooks, which the data scientist can doing the interactive experiment on the data. So why we should put all these things under yarn? This is a normal yarn user. He's very nice and peaceful. And he wants, first is SLAs, monitoring, such as they want the, to get how long the job will run, and typically what's the history, job running time, and the machine status of the clusters, etc. And they want to add in some quotas to the queues and users to limit some queues or users can use only a limited number of resources. Also, they want isolation, so which they don't want their jobs to affect each other. They want their jobs can be run independently. So what yarn can provide for the SLAs, they can do proper capacity planning, so which they can specify the capacities for each queues and for each users. Also, the yarn capacity scheduler preemption, which we can balance the resource usage between queues and users. That means if one queue is taking too much resource, the yarn scheduler will give this resource to the other queues to make sure the other queues can meet their SLAs. Also, the reservation system, which means you can get the resource reserved prior to run the job. Regarding to the monitoring, we have the timeline services which we can look at the history, job running time, and what is the many detailed information of the job. Also, some other plugins such as the Grafana, we can show in some nice graph of the clusters status. Regarding to the quotas, we can specify the queues or user quotas, and we can put the user access controls, which means we can, to limit some users cannot access some specific queues. Regarding to isolation, we have the existing isolation for the CPU and the memory. It is already part of yarn. And what we are working in progress is GPU, FPGA, and network. So I will show one example about how all these things running on the same yarn platform. So let's say we have 5 nodes. We have five nodes here. So each machine has 128 gigabytes. So we put them to all under yarn to manage. We will run some batch jobs like the TEDs and Spark, and some long-running daemons such as Hive LLP, which we can run some interactive queries. The queries can return to you in sub-seconds. Now you have some requirements to running some machine learning or deep learning workload. So the company give you some budget to purchase some GPU machines. We put these machines to yarn to manage as well. And we will run in the TensorFlow application on these GPU machines. Also, we can run some different deep learning frameworks such as Caffe or the MXNet. Yeah, so I will briefly talk about the GPU support on Yarn. First question is why we need GPU support. The reason is the GPU can boost the performance quite a lot. So typically it can boost 10x to 300x of performance compared to running only on CPU. And the reason is the GPU has many cores to handle the massive but relatively simple computation tasks simultaneously. So let's take a brief look at this. So on the right side, your right side, it's a CPU, which the CPU has few very complex cores to handle the very complex sequential logics. But on the left side is a GPU. It has many smaller cores, but for each core can handle the computations efficiently. So let's say we have one neural network program which needs to compute. For the application, most of the time is spending on the computation-intensive tasks, and for the rest of the part is only a small chunk of it's some other things. So the framework says the TensorFlow will map the GPU computation-intensive part to the GPU and the other part to the CPU. With that, the time spending on the GPU will be reduced a lot. So that means the overall running time for a job will be reduced. So without GPU support, we can find the researchers and the engineers are almost impossible to wait for job finish. And if these jobs will run for a couple of weeks. So here are some challenges and status of the GPU support. First is we have different level of GPU support. Currently, what we already provided since Hadoop 2.6 is we have the partitions and node labels to make the some GPU tasks can only go to some of the node which has GPU installed. With that, we can enforce the quota for queues to access to different labels, as well as the accessible control for these labels. But the problem of this solution is it cannot enforce the proper isolation for the GPU. So let's say if you have 4 GPU cards installed in the machine, you cannot give the applications running on this node proper isolation. So one application may be asking for only 1 GPU, but taken all 4 GPUs. We cannot avoid these things happens. So beyond that, what we are building right now is we want some more fine coarse GPU support. The first level is give me the full device only to me, only to some containers running on Yarn for the full life cycle of the container. That means the GPU will assign to the container from the container started, and the container when the container is finished, the resource will return back to the to Yarn so other applications can use. And with this, we will enforce the isolation for the GPU, which means once this GPU assigned to the container, nobody else can touch this resource. The second thing is we want to have the multiple full device. So let's say we have one application needs 2 GPUs for one container. So we can also allocate 2 GPUs to the container. So beyond the 2, we can have the some better isolation. So let's say we can assign the full devices to the container, but the container maybe decide to give up the resource after running for a while. And so, for example, one Spark job could have multiple stages, And for some stage needs GPU, but the other stage didn't. So the Spark job could give up the GPU resource once they finish the GPU computation. The most ideal isolation is the last one, which is multiple applications can share the same GPU device. So there are more dimensions for the isolation, which is the currently if we're using GPU, the GPU has to talk to the CPU or the other GPUs. So that means it will use bandwidth. So we can enforce the resource usage for the GPU bandwidth, which is the PCIe bandwidth or NVLink bandwidth. Or the on-GPU memory is also one part we could isolate. Also, if we have multiple GPUs installed in the cluster, the communication between GPUs is different. So we prefer to allocate the GPUs to one application, which the GPUs should be closer to each other. So what we are working right now is the first two isolation, which is the full devices or the multiple full devices to the containers running on YARN. Yeah, so the next thing I will talk about is how YARN assembly can make everything easier. So previously, I'm not sure if you have looking at any tutorial of YARN before. It mentions something that's how to write in your own YARN application. It's very hard. You have to write in Java code, to write in the application master code. You have to understand every black magic of the resource request. And typically, you will write the first version of the application master wrong. So it cannot even get started. So, but this will soon become history. So what we are working on right now is to have one assembly spec in JSON file format. We call it YARN file. With that, you can define what your application wants. And for example, the logics, for example, the resource of the application, and how many containers you need, the name of the name of the applications, etc. I will go through this for using the later examples. And once you have done writing the JSON file, you can simply do post the JSON to YARN server using the REST request. And YARN will help to figure out the rest of it. So here's an example to run the TensorFlow training using the YARN assembly. So let's say we want to do the TensorFlow training. We first will define the name of the spec. And under the application, we need to define one or more components. For the component name, we define it to be TensorFlow trainer. And the number of container is 1, so which means we only want one container to do some single host training. And specify the artifact, which is the Docker image name, and specify to Docker. So YARN will later figure out to do the Docker pull the image and try to run the job. And then you need to specify the launch command, which is let's say some customized Python script to do the training. Specify some input data, maybe on HDFS or S3, and some list of parameters. And during this training, you could put your final trained model to somewhere, so later you can use that to do the prediction. Also, you can specify resource, how much resource you want. Here you specify 8 CPUs and 32 GB of memories and 4 GPUs. So YARN once receives this JSON spec, it will decide how to ask the resource and how to launch the application. Also, we can use the YARN assembly to run a multi-stage job. So let's say we want to run a job which needs to first using Spark to do some pre-process. Then you want the TensorFlow to do the training after that. So you need to define first component is a Spark preprocessor. And you need 5 containers to run, and the data image name of the Spark. There are some customized Python script to do the Spark, to do the Spark preprocess ETL and specify one input and output and some other parameters if you want. Similar to above, specify the resource of each container. And after this component, it can put another component, which we can call it TensorFlow Training, and put the dependency of the first component, the same name, the Spark preprocessor, and point to the previous the preprocessor component. And after that, you can specify, similar to previously example, you can specify the launch command, the resource, all these things. So YAR will first, when it gets started, it tries to launch the first preprocessor, and once it's finished, it will go to the second stage. Also, with YAR assembly, you can run the distributed TensorFlow training with parameter server. So basically, the other things similar to previous things, these 2 components. The first component we call trainer, and with the trainer we will run a Python script to do to specify the parameter server hosts. So in the YAR assembly, we will have the new DNS mechanism, which for each job, it will have one unique DNS entry for each launched task. So with that, you will know the host name prior to launch the job. So which is the component name, job name, username, and some customized domain name. For the trainer job, it will specify the parameter server host and the worker hosts. Yeah, and similarly for the parameter host, it will launch but specify the job name to be parameter server. Also, we can do the parallel parameter training, which is, let's say we want to train multiple models concurrently. And for each model, we need to specify different parameters. So we can specify different components. The first is specify the learning rate to 0.1 and optimizer to gradient descent. And the second one is to use the optimizer to be ADEM and with different number of steps to train. Finally, I will talk about how YAR assembly to do the model serving and how we can update the model. So basically, we will define one serving component and specify 10 containers to do the model serving, and to do the serving with a port and what's the model name. This is all customized script. With the DNS, we will know the entry will be serving.tensorflow model serving, username, domain name, and port to access the service. And YAR in the backend will do the load, could do the load balance for launched instance. Also, with the recent feature added to YAR, we can do the in-place model update, which means when you want to update the model, you can relocalize the resource in YAR container and restart the service, which you don't have to re-request the container with less latencies. Yeah, so I will hand over back to Yanbo to talk about an example what's through, how to do the click-through rate on a big data platform.
Okay, can you hear me? Okay. Okay. Thanks, Wangda and Yan help give us so strong ability for the data scientists and machine learning engineer can solve their problems. I will show very, very tiny examples about CTR prediction in big data platform. Oh, sorry. First, give a very brief introduction about what is CTR prediction. CTR is almost the most profit or most successful business model during the past decade, such as Google, Yahoo, Bing, or Facebook, has earned money from CTR. And in general, it's giving a user and advertisement and context. You will predict whether user will click this advertisement. But the CTR prediction problem for machine learning engineer is very, very challenging, such as the challenges include the click sample is always very, very small, compared with almost all the samples are not clicked. It's data clue. And every day you will produce, the website will produce a lot of data. So it's hard to train the CTR prediction in a single machine. So we need distributed machine learning. And we have some limitations at serving. It means when a user come to our website and we need to respond corresponding the most possibility for the users to click. So the responsible time should be very, very fast. So this is very, very challenging. We can say this is the data format of the CTR prediction. The impression is actually a log when a user browse or click or search in our website, and then we have a log whether he or she clicked our advertisement, and then we will join the data with user and advertisements database and to generate a web table. And for the CTR estimation model, is usually the linear model is still the major models for CTR estimation. Since I just mentioned the CTR data is very, very large, and to train a nonlinear model maybe can't finish in a reasonable time. So, but the research or engineer from data scientists or from machine learning area still to explore some nonlinear model, such as gradient boost tree or deep neural network. But currently, the hybrid model is still the most useful or most better suitable for this question. Let's say a very simple example. Okay. Maybe I can make myself. Okay. Can you see the? Oh, I think it's clear. This is the UI of Zeppelin. Zeppelin, you can say, it's an interface for the data platform. You can write some code in the Zeppelin website and to call some data from stored at GFS using Hive to query some data using Spark, or even we can use some single machine libraries like TensorFlow or Distributed Tensorflow. Okay. Let's start with the simple. You can say the first step. Usually the data is generated like Flume or like Kafka. The data is flowed into HDFS, and the most possible format for the data is ORC. So we use Spark to load the data, and Then we will to do a group to a statistic for the click or non-click users. You can see here, the click and non-click count is usually unbalanced. This is if you didn't encounter such problems, then I can say you don't do some real machine learning problem. It's usually very unbalanced. So the first thing we need to sample some data from the data set, the group which have more users. So you can say we can use Spark to sample from the click, the group that don't click. And you can say maybe 50 multi-times for the click group. So we can sample the data and union the data together. Then we got a new data set. The label, the positive label and the negative label are currently are balanced. So if the positive and the negative labels are not balanced, you can't get a better result for the model training. And then we will join the click data with advertisement and user data. And the advertisement data like the campaign type or the location of your advertisement in the whole web page, or even some image data, such as your advertisement may be image. And then we got the join data. Currently, we didn't select image data. We only show a simple example. So we select several columns from the data. And then usually the data is very noisy. We need to drop some non-value from the data set. You can say in my data set, there are about 4 samples, 4 instances on non-values, so we need dropped. Okay. And after that, it's very easy to split the whole data set to training and test data. And then we can save the data set on HDFS for different subformat. We can save as CSV format or save as the TF records format, which is specified to TensorFlow. And then we can start a new demo to train a TensorFlow model. You can see here. The detail, I will not show the detail. So you just say if your data scientists or machine learning engineers who use your platform want to train deep neural network, they can write some code like here, and then they can train a model. After that, if your team has some requirement for training a model with other tools like Spark, you can also write some code here, and then train a linear model with Spark. So after that, the notebook can be shared between different data scientists and engineers. You can click the export button to export the notebook to other data scientists or machine learning engineers. Then they can use the. All of these are powered by by the Hadoop ecosystem. Okay, I think I finished our talk. Any questions? Oh, okay. I will share the code at GitHub. Okay.
JSON yarn assembly example. I noticed you specified those, but can you also just put the node label on there?
Yeah. So basically, the question is, can we specify low label on the yarn JSON file? Yes, we can specify the low labels and the other properties in the JSON file. Yeah, so I think our time is up. So for any other questions, we can discuss on the hallway. Thanks everybody for joining.